Welcome to oral presentation 4 of Senior Design Team ME50, a portable LED-powered, fiber optics-assisted marine industrial illuminator. Our company sponsor for this project was Mr. Giovanni Tomasi of RSL Fiber Systems in East Hartford, Connecticut, and our faculty advisor at UConn is Professor Jackie Sung. This will be our final presentation. Today we will be giving an overview on our work, as well as a projection on the work that would have occurred had our lab not closed for the semester. We will be giving a summary of our project's problem statement, the analysis that we did in preparation, and the testing simulations that were conducted. And then we will talk hypothetically about the outcomes of the project. This will hopefully serve as a foundation for a future senior design team tasked with continuing the project in future years. This image is an old example of the illuminator systems that RSL Fiber Systems creates. Our team is tasked with just creating the illuminator box, which you see on the right side of the image, where the light is actually created for the system. These devices operate in hazardous and often inaccessible places. Currently, military vessels and industrial sites use illuminators that are extremely robust by military standards, but are not light, not portable, and not suitable for temporary applications. There were two main criteria for our improved design. It must be lighter in weight and more easily portable, because systems are currently around 25 pounds and are not internally space efficient for manufacturing reasons. The second criteria, they must maintain original specifications of lumens and naval requirements, including shock, EMI, waterproofing, and Navy coal regs. The biggest anticipated challenge that we faced was making the illuminator entirely waterproof, and thus no air could be used to actively cool the heat-generating LED. We tested and simulated many ways to remove heat from the LED, without air transfer into the illuminator unit. Our device in practice is very simple. It only creates light. However, this is a more complicated process than you would expect. In our design, heat is produced mainly from light generation in the LED, and also slightly from the internal battery. For waterproofing reasons, there was no convective heat transfer through the air from the LED to the heatsink on the outside of the system. This was mainly done through just heat piping inside. So this simulation for the heat transfer calculation will only be from the external heat plate to the air. Before any full simulations were conducted, preliminary paper calculations were done to give us a rough idea of the components necessary to cool our system. This is a general overview of the equations necessary for heat transfer calculation. The rate of heat dissipation was actually known for our LED, based on the information given to us from RSL Fiber Systems, so our goal here was to estimate really the size of the heat sink that was necessary to give us the appropriate heat transfer rate to the air. We used known physical properties of metal and air, and examples of airspeed and ambient temperature that were realistic but more difficult for achieving necessary heat transfer. Using an average-sized heatsink, our theoretical data gives a cooling power of 40 watts, which is 130% of our heat generation data. This means that given suboptimal working conditions and a relatively small to average-sized heatsink, we can still successfully operate.
This slide shows the CAD model for the internal components that we'll be using in our prototype. Inside the enclosure, we have a small aluminum plate that would sit on the back of the LED, which is located to the left of that corner junction. As it conducts the heat through the back of the LED into itself, the heat will be conducted through a series of heat pipes extending laterally from both ends of the plate, which then go through other aluminum junctions and connections to conduct the heat through the wall of the enclosure itself to the heat sinks mounted on the outside. Now, these heat pipes come off the shelf as per the sponsor's request. All 9 are the same, but these aluminum connections and junctions will need to be machined, but are very minimal. Moving on to the external CAD model of our prototype, we have 2 heat sinks mounted on the outside walls of the enclosure. These would be located right on the outside of where the aluminum connections are found on the inside of the box, therefore conducting the heat straight through the walls of the box, which are made of aluminum 5052, to the heat sinks, which are made from extruded aluminum. These two heat sinks are the same type, which can be found from an off-the-shelf vendor. They're not custom made. However, they will need to have some slight modifications in order to fit our enclosure with these clamps that hold the lid down for our IP65 rating. The only modifications that these heat sinks will need are to have these cuts machined into them so they can fit the clamps, as well as any fasteners that we have connecting it to the enclosure. Now we will also have these heat sinks and connections fastened to the walls of the box with a thermal adhesive in between the flat surface of the connection or heat sink and the wall to maximize the contact area of the components and in turn maximizing the heat transfer through the object. We were considering using thermoelectric coolers and possibly a fan on the outside of the enclosure to increase the thermal conductivity even more. But however, the ECE team was a little behind schedule, and to compensate for that, our goal is to complete this design with natural convection instead. Here we have our ANSYS IcePack simulation results. This picture shows the results of the CAD model shown previously, put through the simulation testing. Our maximum ambient temperature that this prototype needs to function within is 50 degrees Celsius. So we designed our model to be able to withstand and stay below the LED shutoff temperature using that ambient temperature. Assuming that everything below, it should be able to function properly. Now this data shows that the highest temperature within the enclosure, which is at the LED itself, is at just above 67 degrees Celsius, which is a few degrees below our shutoff temperature of 70 degrees Celsius. So assuming that all this is correct, this shows that our prototype design would work under our maximum environment conditions. Also, the simulation was run only using natural convection, since we do not have any fans or any forms of forced convection within this model. The only airflow was allowed on the external side of the box through the heat sinks. There's no airflow going through the enclosure itself.
We ran multiple tests with thermocouples to see exactly how much heat we would need to dissipate from our LED. Our 3 tests consisted of tests with the LED fan running, one with it not running, and another with it running. However, the LED was placed in our enclosure with the top sealed shut. For our first test with our fan running, the heat sink stayed at a steady 15 degrees Celsius, while our LED temperature maxed out at 25 degrees Celsius after 15 minutes of running. For our second test with our fan off, the heat sink and LED gradually rose to its shutoff point of 70 degrees Celsius. It took a little over 10 minutes for the LED to reach this shutoff point. When running the LED fan within the enclosure, the temperature tops out at 46 degrees Celsius. This is without any external heat dissipation. The walls of the aluminum enclosure were warm but not hot. Also, one thing to be noted is the light of the LED was shining inside of the box, making it hotter inside. If the light was allowed to leave the enclosure like it would in the final design, then the temperature within the box should be less than 46 degrees.
The risk possibility matrix for this project is composed of many risks that we anticipate more of in the future, and ones that we've already encountered during the course of this project. The main one that we've already encountered is the delays due to the lack of communication between mechanical engineering and electrical engineering teams involved in this project. This has caused some hang-ups in the progress where we haven't been able to work necessarily, and the solution that we've decided on was to talk more openly, realistically, and sometimes aggressively about our schedule and what we need to get done as each individual member of this group. The second risk that we encountered was scope creep on the company's side. They weren't always consistent in their direction and often flip-flopped on the tools with which they wanted us to work, as well as the deliverables. This was mainly a concern for the electrical team, but the delays on their end meant that we had less of their designs to work off of, and thus caused more delays. Similar to what we learned with working with the electrical team themselves, we decided that we needed to be more realistic and set clear expectations firmly with the company regarding their original plans and deliverables. Moving on to some of the future risks for our product, we worried that moisture might still have the possibility of damaging the supposedly waterproof system. I was drawing on RSL's past experience working with products and clients using the products. We decided that it would be important to make it easy for the client to work on the product themselves if they needed to. For instance, they would want to be able to apply their own adhesives or waterproofing solutions to specific places on the unit that would be more prone to leaks getting into the system. Another problem that we thought to anticipate further in the future was delays in part orders. We actually had a pretty significant problem in our project where we ordered an enclosure and expected it to come back during spring break where we could work on it afterwards, so we didn't feel like we were not using that time efficiently. However, after we had already ordered the product, the company didn't fulfill their delivery for us, so we realized that we would have to go back and purchase another one. From this experience, we learned that it's important to have many different options for parts to source so that when something unexpected happens, like a cancellation of a delivery, we could have a quicker turnaround where we could order another part that we knew would work very quickly. Another problem that we anticipated was that the system might just not dissipate enough heat for what the LED is generating. This is a bit of a stretch, but we thought might happen was the LED's dimming function could possibly be used to draw less power from the LED in situations where, say, the air is very hot or dry, because this would make it harder for heat to leave the system. So far in the project, we have acquired hardware from the sponsor's previous product iterations and used it to create a successful design of our own. We have taken measurements on our LED unit, run accurate simulations to validate our thermal calculations, and ordered the remaining parts to construct a prototype illuminator. Unfortunately, of course, our access to the ME lab has been restricted, and we will no longer be able to complete our finished product. As unfortunate as this is, Team ME50 is very proud of the work that has been done so far. The remainder of the semester would have been spent assembling the illuminator enclosure and incorporating the electrical team's PCE boards for controlling the electrical systems. We would have prototyped and redesigned the illuminator to account for flaws and arrived at our finished product. Our results suggest that our design was going to be entirely successful, and most importantly, we would have a finished product by demo day, barring the results of our IP and shock testing, of course. We consider this project a complete success and an incredible learning experience in professional engineering.